In my experience, it seems to me that in the history of signal integrity issues on printed circuit boards, we've gone through 4 stages. The first stage was kind of trivial. There were no signal integrity issues on circuit boards. It was truly a connect the dots kind of technology. In the second stage, we began to run into problems from inductance that occurred on the board, both in the traces and in vias. And this began to cause some signal integrity issues. In the third stage, we began to run into problems where resistance began to vary with frequency. This comes about through things like the skin effect and dielectric losses that look like resistance is varying with frequency. That's not exactly true, as we will discuss, but it looks like it. And this raises a different kind of set of problems for signal integrity. And then the fourth stage came about when we started dealing with signals with very short wavelengths. So short that any solutions that we came up with for the problems in the second and third stage are difficult or impossible to implement because there simply is not enough physical room. Now, as I said, in the first stage, there were no particular issues. In the second stage, when inductance began becoming a problem, the problems that came about were EMI, crosstalk, ground bounce, which we will talk about, and the solution to that, or at least part of the solution to that, is bypass capacitors. And so the whole topic of bypass capacitors and power distribution system design comes into play here. And then fourthly, reflections, controlled impedance traces, transmission lines, and terminations, and so on. So these 4 sets of problems started raising their heads when we began running into problems with inductance on the boards. Resistance varies with frequency. That's when skin effects started coming into play, dielectric losses started coming into play, and the primary impact of these 2 things is lossy transmission lines. In the second stage, we were able to treat transmission lines kind of as ideal lines without any losses. But in the third stage, we begin to have to be concerned about lossy transmission lines, and that raises a new set of problems. And then finally, as I said, in the fourth stage, with very short wavelengths, there's just not enough room to implement the solutions. Even the time through a via becomes an important parameter and something we need to be concerned about, or maybe even change our design because of. Now, the thing that is taking us through these 4 stages is faster and faster rise time. Not so much frequency, as we will talk about as we go through these lessons, but faster and faster rise times. In the early stages of printed circuit board design, we were dealing with relatively slow rise times, and there was really nothing going on at the board level. But as rise times got faster, then we needed to worry about EMI and crosstalk and so on. As rise times got faster yet, we had to be concerned about skin effect and dielectric losses. And finally, when rise times get really, really fast, and therefore wavelengths get really, really short, we start running into the problems of via lengths becoming significant, via lengths becoming longer than the critical length, and so on. So faster and faster rise times is what is driving us through these stages. Now, individual designers may be at any one of these stages, depending on the technology you're using and depending on the technologies that are common in your particular industry. But even if you're working in an industry which is kind of back here in stage 2, sometimes you're stuck with buying components that are designed for stages 3 and 4, and those components can cause problems for you related to these more advanced stages, even though your industry really isn't at that stage yet. So no matter where you are on this spectrum, you do need to be concerned about the entire scope of signal integrity issues on circuit boards to know about potential problems that you might run into. Now, the lesson relationships go kind of like this. Lesson 1 covers background information. And a lot of this you will know, but I'm pretty confident that there are things in these first 6 lessons in the background information stage. There's a few things that no matter who you are, you haven't heard it all yet. So I encourage you to stay with it and listen through all these stages. It is important background information for what follows. Lessons 2, 3, 4, and 5 relate to things that are going on in stage 2. Lesson 2 is eliminating reflections. This is about transmission lines and controlled impedance traces. Lesson 3 talks about EMI and crosstalk and how to deal with it and control it. Lesson 4 is focused specifically on differential traces, and I give you my set of design rules for differential traces. Lesson 5 talks about the power distribution system and the problems that can occur, and particularly the solutions that we can employ using bypass capacitors and the role of ESR and so on. Lesson 6 deals with resistance varying with frequency, skin effect, and dielectric losses. Lesson 7 deals with what happens when we have really short wavelengths. How do we deal with vias that are longer than the critical length, and so on. Lesson 8 deals with the relationship between trace current and temperatures. This is not normally thought of as a signal integrity issue, but it is a board design issue, and I kind of thought it would be good to include this along with the rest of the package, talking about the relationship between trace currents and temperatures and fusing currents on traces and so on. And then in Lesson 9, I give you some final thoughts that I have about all of the topics that we've covered up to that point. Now, you may be aware that recently in 2013, I published my second book, PCB Currents, How They Flow and How They React. And there is some relationship between the lessons in this package and the chapters in that book. And they go kind of like this. Lesson 1, the background information, covers stuff that we cover in chapters 1 and 2 in the book. Reflections are covered in chapter 17. Minimizing EMI and crosstalk is covered in chapter 18. Designing differential traces specifically is covered in section 17.9 in the book. Distribution problems is covered in chapter 19. High-frequency resistance losses in chapter 20. Dealing with really short wavelengths is covered in chapter 21. The relationship between current and trace temperatures is covered in chapter 16. And then in the book, I have a section on final thoughts. It might be helpful to you as you go through these lessons to have a copy of the book handy. Or after you finish the lessons, it might be nice to have a copy of the book for reviewing some of the same topics. The information is not identical that's in the book and in these lessons, but it's certainly complementary, and I recommend you have the book available too.